The traditional measure of performance in schools is the A to F report card. In recent years, the American Society of Civil Engineers has applied this grading system to America's infrastructure of buildings, roads, and bridges. Based on these report cards, the overall grade has been a D. At UNC Charlotte, civil engineering researchers within the Lee College of Engineering are working to develop new and innovative solutions for improving America's failing infrastructure. The Structures Research Group is focusing its efforts on built structures, materials, and infrastructure. One of the researchers within the group is Dr. David Young, who is also the chairman of the UNC Charlotte Civil Engineering Department.
In 2001, the American Society of Civil Engineers, or ASCE, expanded some work that had been done 10 years earlier in evaluating the nation's infrastructure, the condition of our nation's roads and bridges, waterways, aviation systems, energy systems, water, wastewater treatment, transportation systems, and so forth. They evaluated each of those categories by surveying engineers, consultants, managers, public works officials around the country, asking for their observations and opinions about the nation's infrastructure. They collected all of that information and issued an overall report card grade on the infrastructure, giving a grade of D. They repeated that process in 2003, and we improved slightly to a grade of D+, but they also estimated a need for $1.3 trillion to repair the nation's infrastructure. This past March, they issued the 2005 report card on the nation's infrastructure, giving a grade of D, and estimating $1.6 trillion needed for repairs. Many of the items addressed in the infrastructure report card are inherently civil engineering items. So we teach and research those items on a day-to-day basis. 3 years ago, we decided to address those items in more detail and with more intensity, and we proposed a PhD program in infrastructure and environmental systems. That program was awarded to UNC Charlotte, and it started last fall in 2005. In that PhD program, we will focus on advanced studies and higher level research addressing the needs of the nation's infrastructure and environment. One of the key aspects of our program is our structures group. That group of 5, soon to be 6 faculty members teaches and researches in the areas of materials, structural design, structural evaluation. A key player in that group is Dr. Janos Gergely, whose interests include high-performance materials, concrete and masonry materials, and looking for ways to use high-performance materials in strengthening and repairing structures.
The primary purpose of Dr. Janos Gergely's high-performance materials research is to be able to renovate existing structures instead of tearing them down and starting from scratch. Such renovations can be made quickly and at lower costs. And because of the advanced physical properties of the high-performance materials, the renovated structures are actually stronger than they were originally. Dr. Gergely's current project is the testing of a full-scale masonry building reinforced with carbon fiber. Researchers involved in the project include faculty, graduate and undergraduate students, technicians, and a colleague at North Carolina A&T. The test structure is instrumented with about 100 sensors that record the stresses applied by the load frame. Computers record all the data, telling researchers exactly what amount of force it takes to cause the building to fail. The test itself involves applying a side load that simulates the effects of an earthquake. The results are then compared to data from tests on buildings that did not have carbon fiber reinforcement. To date, the test has shown that the buildings gain a significant increase in lateral strength with just a small application of high-performance material. Another project in Dr. Gergely's structures research is the evaluation of existing bridges and the use of high-performance materials in bridge decks. The research is sponsored by the North Carolina Department of Transportation. Testing has been performed to evaluate the construction and performance of a glass fiber reinforced polymer composite bridge deck built in Union County. Tests show the new bridge deck to be stronger than a conventional concrete and steel deck, even though it is 50% lighter and took 1/4 as much time to construct.
The bridge research conducted in the Structures Lab is very important to improving our nation's infrastructure. For example, many bridges in North Carolina and across the nation are experiencing traffic flows far in excess of those for which they were designed 20 to 30 years ago. We must be able to estimate their capacities, we must understand their remaining service life, and we need to develop methods and materials for extending their service life. Along those lines, another one of our structures researchers, Dr. David Boyajian, focuses his efforts on materials and their deterioration. He's particularly interested in why materials corrode, how they corrode, and how do we stop it.
The research of Dr. Boyajian also involves advanced materials, namely composites, which are combinations of two or more materials that produce another material with advanced engineering properties. Such materials have been used in the aerospace industry for up to 50 years, and in the last 10 years have found their way into civil engineering applications. Dr. Boyajian's work with Dr. Gergay involves replacing steel rebar in concrete bridge decks with a composite plastic rebar. In a laboratory setting, Dr. Boyajian and his students are looking at the durability of a new rebar material that will be used in the construction of a bridge deck in Macon County. The deck will be the first of its kind in North Carolina. The experimental plastic rebar is first embedded in concrete and then put in an alkaline solution that simulates high alkalinity. Heat is applied to simulate the greater reactions that take place over time. The testing helps determine how the material will perform over the next 20 years and the loads it will be able to withstand. In a second project, Dr. Boyajian is looking at the external reinforcement of bridges using carbon fiber. Specifically, his research looks at the bond between the carbon fiber and concrete. When composite material is applied to the outside of a bridge, the bond with the concrete is exposed to a continuous series of stresses. Dr. Boyajian is using a unique fracture mechanics approach to study the bond between the composite fabric and the concrete. With the test fabric bonded to a concrete member, the bond is fatigued and eased literally millions of times to simulate traffic loads. Results are showing that the bond is strongest when the concrete surface is rough as opposed to smooth. The analyses being done by UNC Charlotte Structures researchers is showing that the use of composites in strengthening bridges is the wave of the future. It is significantly cheaper and more efficient than rebuilding bridges and results in bridges with improved performance capabilities.
In addition to the high-performance materials work being conducted by our Structures Research Group, we have a faculty member that's also looking into materials and components that are resistant to natural and man-made disasters, such as earthquake, hurricane, and terrorist attack. Dr. David Waggle brings his experience from industry and academia into this Structures Research Lab, where he focuses on the response of building systems and components to natural and man-made disaster. He is currently evaluating building systems and components and their response and behavior to blast and explosion.
Dr. Waggle's research is part of the Civil Engineering Department's overall enhanced capabilities in homeland security. His work is specifically aimed at making structures more resistant to terrorist attacks. One of the structural components Dr. Waggle is analyzing is the large glass windows or window walls used in skyscrapers. To determine how the windows will react in a blast, they are mounted in the UNC Charlotte load frame. They are instrumented to record data on the stresses, and force is slowly applied until the windows break. In blast scenarios, the blast loading itself lasts only milliseconds. It is followed by the detonation products, fire and hot gases, which last for tenths of seconds. The combined loading can be hundreds to thousands of times higher than those of the worst hurricanes. There is tremendous variability in blast loading. Fragmentation and shrapnel effects are very difficult to predict. Structural response is complicated by structural members and non-structural components that are often pushed to their limits. All these variables combine to make blast evaluations multi-layered, challenging problems. In addition to window walls, Dr. Waggle's research includes investigating the behavior of building structural systems, the building envelope, and perimeter barrier walls when subjected to terrorist bomb blasts, impacts, and ballistics. For all these elements, they look to see if the structures are strong, ductile, and redundant enough to withstand an attack. The minimum goal of the research is to ensure the structures are strong enough to protect life.
As a member of the civil engineering faculty, I am also a member of the Structures Research Group, and I focus my research on new materials and new systems for primarily residential and light commercial structures. Those materials include high-performance composites as well as composite sandwich systems comprised of various traditional materials.
Dr. Young's research is in the development and application of composite construction materials known as structural insulated panels, or SIPs. The panels represent a rapidly growing industry for use in the construction of residential, light commercial, and institutional structures. Although recently more prevalent in the western United States, with the help of the UNC Charlotte Structures Research Group, they're now finding their way into more applications east of the Mississippi. The basic concept of SIPs is to take an interior wall of sheetrock or other material and put it in a mold opposite an exterior wall of stainless steel, aluminum, plywood, or similar building material. Once in the mold, foam insulation is injected between the interior and exterior material, forming a completed wall or sandwich panel. The research of the Structures Group begins with testing the individual materials used in the SIPs. It continues with evaluating every possible skin and insulation combination. Every type of load capacity and connection method, as well as the material and panel reactions to heat, cold, and ultraviolet rays, is tested. As a result of the research, a number of advances have been made in determining which SIPs work best for a variety of building conditions. Improvements have also been made in foam application techniques and construction methods. To date, the research has shown SIPs to be very strong with load-carrying capacities sufficient to satisfy many building codes. The materials also have amazing insulation properties. By determining the proper uses for SIPs, the Structure Research Group is helping to put this new, economical, energy-efficient building product into the marketplace.
The students and faculty in the Department of Civil Engineering at UNC Charlotte are actively engaged in teaching and research in many of the areas addressed by the ASCE Infrastructure Report Card. We've looked at one example, our Structures Group, and the research activities in which they're involved. The results of that work will greatly enhance our nation's infrastructure in the future and will raise the grade on the Infrastructure Report Card.